All right, good afternoon. Sorry about my delay here. I made a last minute change on the PowerPoint file and then rushed over here, but I uploaded it Moodle first and then turned my computer to sleep, my office computer, and it didn't upload sense of how much gas does it take, how much energy does it take to operate an aerator, for example. So we're going to take a look at a bit of stuff about the flux of gas from an atmosphere or from a gas phase into the water. Got a couple slides on the flux and a couple example problems that we're kind of just using Henry's law. And then we'll take a look at more so the dynamics of how do we map the math into a system where we are aerating. But you could look at different math if you're, let's say, doing like raining water through an air stripper tower to do an exchange that way. The physics of it would look a little different. Anyway, we're going to come back kind of building from last time and just focus in on what is the flux of our gas species across some surface area. And we have this table here, and really what we want to understand is that the flux of a gas across some surface is effectively the rate of transfer of the gas that we'll get. So if we define the rate of transfer here, we could say that this is going to be the flux of gas into the liquid times the area divided by the volume for some particular packet that we were talking about last time. So we can take a look then and pull into that analysis the packet idea. Packets in a PFR type of scenario, have some math for that. Packets in a CSTR, and we could get into all sorts of physical descriptions or models that describe these different physical cases. But the most general case we can look at here at the top would be for any situation of how long that little packet of water is near the surface. We could describe it as the tau, so the residence time for that packet in the liquid divided by these guys. So just kind of the point of this is to show you we can handle the different scenarios for how the mixing is occurring and relate it to the flux. Perhaps we're doing a flux as a mass balance accounting for diffusion, or accounting for this, or accounting for that. A thick packet, a small packet, a short time there, a long time there, all that. Okay, so we're not getting, I'm not pointing you to this and say, hey, solve this right now. Just showing you that this level of detail exists and we could work with that. A little more practically, we can say that, well, as a flux, for fluxing gas into the liquid, that's going to be the reverse, the opposite, the negative of the flux of that gas into the gaseous phase. We can describe then that as the JL equals negative JG. Okay. So when we average some flux, we could describe it as this flux equals some constant for that liquid interface times the concentration of the liquid in a initial state minus the concentration of the liquid at some second state, B we'll call it. So if we define it this way, we can kind of say that there's going to be some exertion of, not pressure exactly, but a driving force of concentration going into the liquid based on the difference between what concentration the liquid would like to have if it was at equilibrium with our gas and where we currently are. So we can end up defining this liquid phase gas transfer in that sense. And so this KL will be that liquid phase gas transfer constant, or a mass transfer coefficient. Okay. So a way we often will describe this, we'll just say in the overall picture, and this is kind of ahead of myself a little bit, the overall picture, we're going to say this is a uppercase K, overall gas transfer coefficient times the CL star minus CL at some other point B. And this is our equation that perhaps we can use. So this would be the flux of gas into a liquid with an overall constant times, here's the concentration at equilibrium. That's the concentration of this gaseous species in the liquid. That's what the L is telling us. It's in the liquid. The star is saying that, hey, this is what we'd get at equilibrium. And then this other piece is some current moment or current situation, or maybe some other location in the system. Okay, so then we have this driving force times, or this concentration differential times this overall constant, ultimately gives us that driving force and flux. So we can also describe this overall gas transfer coefficient by saying this should be the lowercase kl times the lowercase kg times the Henry's law constant divided by kl plus kgh. So there's probably some derivations you could find in the book, fleshing that out further. But essentially, we're getting, we have a way to handle what is this overall constant coming from. All right, so another thing to keep in mind, this gas transfer is effectively a rate per unit volume. And that concentration of the surface area itself, this AR, is key. So in this case, that rate of gas transfer is going to be driven by this overall constant times the surface area times that differential, if we want to get the rate instead of a flux. So we can convert from the flux, which would be kind of a speed at which gas is transferring, so a flow rate per area type of deal. Well, then we can account for the area. So if we have bubbles, that's the surface area of each bubble times how many bubbles we have type of deal. If we account for that, then we have the total rate. Okay, so not bothering too much with the derivations and stuff. If we just kind of set that aside for a moment, which I have done, we can see that, okay, we've got the flux, got a driving force for it. If we take flux times area, we're going to get an overall rate. Okay. So if we elaborate a little bit, we could say, so the corresponding value here for this gas transfer per unit volume of solution, we could get that, can compute that by multiplying this rate by the ratio of reactor volume to the aqueous volume, or substitute that AR for AL. So essentially converting from the surface area of, let's say, the bubbles in a given volume of my water to the surface area of bubbles in the total reactor. That's what we're doing. So we can easily convert to the rate of exchange in the entire reactor that way, is all it's saying. So this is just rate in let's say, a specified, or no, arbitrary volume to rate in the total reactor. Okay, so kind of self-evident, I think, but we can make that conversion. All right, so let's take a look at a problem and see what we think. Might step through the books solutions on this, or on some of them today, but let's take a look and see what sense we can make of it, thinking about it in terms of that flux concept. So this problem says droplets of groundwater, half a millimeter in diameter, containing 3 × 10⁻⁵ moles per liter of carbonic acid and 4 milligrams per liter of oxygen are sprayed into the air. The value of KL for both constituents is 0.05 centimeters per minute. The temperature for both air and water is 25 Celsius. Partial pressure of oxygen and CO2 in the air are 0.21 and 0.00031 atmospheres respectively. The question then says, what are the initial rates in moles per liter per minute, and directions into the droplet or out of the droplet for CO2 and oxygen transfer. It says assume that the solution pH is low enough that ionization of H2CO3 is negligible. Okay, so there's a lot there. Big questions, it feels like, in a quick little problem, or a quick looking problem. So first of all, remember that H2CO3, this is going to be in equilibrium with CO2, right? This is what we get when we have CO2 plus H2O. So we can get essentially CO2 gas from our H2CO3. The note about the acidity, that's describing when we could ionize and convert to HCO3-, so bicarbonate, and if we go further to carbonate, but we said none of that's happening, or effectively not. Okay, so we're pretty acidic. Probably have to be pH 3 or so, somewhere around there to make that happen. Okay, give this a couple minutes and see what you think. Sorry. All right, how are you feeling about it? Not feeling it? Somewhat feeling it? All right, so let's take a look. I went ahead and kind of started a bit of it, including giving you Henry's law constants for oxygen and CO2. And essentially what we need to do here is compare the expected liquid concentration if the drops are at equilibrium and compare that to their current state. So we're spraying them into the air, therefore they are being allowed to equilibrate with the atmosphere. And if you take a look, that atmosphere is pretty typical. 21% of the atmosphere is oxygen and about 300 something parts per million CO2. So the, just with that, you might say to yourself, well, oxygen typically has a solubility of somewhere around 8 to 10 milligrams per liter, maybe 7. But I think, just at a look at it, just at a glance, 4 milligrams per liter is probably undersaturated. So probably oxygen will be entering the bubble, and we have to figure that out, or not the bubble, the droplet. For the CO2, I'm not sure. We'll have to check that out. But I went ahead and began the process. Okay, we convert the oxygen from milligrams per liter to moles per liter, so we could take a look. And then, so now we have the concentration of the liquid phase oxygen. Now we need to know the concentration of the gas phase oxygen. We can get that with the ideal gas law, PV equals nRT, and then use that to make our comparison, use that in conjunction with the Henry's law constant to make that comparison. From there, we can make the comparison for both of those, and we can also use that information that we derive to figure out the concentration differential here that will drive our flux. So our flux being this overall gas transfer constant times that differential. And we can convert that into the rate by using this surface area concentration. And just as a reminder, I put over here, this is really what we're referring to as the surface area concentration. So the surface area concentration would be the surface area of a droplet per volume of a droplet. And we could set that out to a bigger volume, to the volume of whatever reactor we're talking about, but we're not given any of that. So we're just going to keep the flux into a droplet, essentially. So that surface area concentration, if we assume it's spherical, the surface area would be, surface area divided by volume, it simplifies to pi d squared divided by pi d cubed, pi d cubed over 6, which will ultimately give us pi over 6. Okay, so setup so far tracking. All right, so I'm going to bring up the book solution and we'll kind of go through it from there, but I wanted to kind of just bring some first impressions to you off the cuff. Okay, so we need to solve this for both oxygen and CO2. I started with just oxygen, but we can use the Henry's law constant for both oxygen and CO2, setting it up to say the concentration at equilibrium will be the pressure divided by that Henry's law constant. So we're given pressure for both. So if we use the Henry's law constant as the pressure per moles per liter, then we are good to go to calculate the equilibrium concentration, the C star in the liquid for both of these. So that's where the book starts, and we get for the CO2, 2.73 times 10 to the minus 4 moles per liter. Assuming that was the oxygen, and for the CO2, 1.05 times 10 to the minus 5th. Now we compare those to the current or the actual concentration that we were given in the liquid phase. So the initial DO, we go through that calculation, 1.25 times 10 to the minus 4th. moles per liter. We compare that to what we find up here, and sure enough, there's more at equilibrium than in the actual groundwater, which kind of makes sense also because groundwater, if anything, should probably be undersaturated. There are microbes and things and minerals that might consume oxygen, whereas in the atmosphere, we are in the atmosphere when we spray the bubbles out. Okay, so we're not going to produce any oxygen in the ground. Rather, we might have some consumption. And so here we are. We would, from that alone, say the oxygen should be traveling from the atmosphere into the droplet. So that's the direction of that flux. And that's what the describe here. So ClO2 is less than Cl star of O2. And then we can take a look at how the CO2 turns out. And let me just draw this a little clearer. So that comparison there. And it turns out that the concentration of CO2 in the liquid phase is higher than it's supersaturated. So it's higher than it would be in our equilibrated water. So then that means that our direction of transfer of CO2 will be released from the bubble. So maybe it's groundwater, or maybe it's a can of soda. Spray some bubbles out and you're going to have CO2 coming out. Okay, so then we go on to the assumption that they're spherical. We can get the surface area of a droplet divided by the volume of a droplet. That'll give us our surface area concentration, this AL guy. And calculate that, that becomes, so 6 divided by 0.5, that would be in per length units, we get 120 per centimeter. Kind of a weird unit, but that's our surface area per volume. Okay, then we can take this rate equation. I drew that up for you, right? The R, this is where we started today. R equals KL times AL times that difference between equilibrated and current concentration. Put in these numbers that we have. We were given the KL. We just calculated the AL, and we just put in the numbers. Okay. From there, we would get a rate for oxygen transfer of 28.4 milligrams per liter per minute. And for CO2, we would have, we're going to express this one as a negative because it's leaving the liquid. We would end up with a negative 5.1 milligrams per liter per minute. Okay, and that's just convention. That's what the thing wraps up to say. It's positive for this oxygen, negative for the CO2, because it's in reference with gas entering the liquid. Okay, does that make sense? All right, a little simpler than I was making it out to be at first, right? But there's a lot of moving pieces in this little problem here. Right? It's like one little paragraph, and there's a lot to it. Okay, another problem to take a look at. So if we have a solution at 25 Celsius containing 4 milligrams per liter of DO, dissolved oxygen, it's being bubbled with air. Instantly, the gas supplied is switched from air to pure oxygen. So air being 21% oxygen, now we have 100% oxygen. All other system parameters, the rate of gas injection, bubble size, all that remain the same. Assume that the total pressure in these bubbles is 1 atmosphere. Throughout the process, to what extent do you expect the rate of oxygen dissolution into water to change at that instant? So what is the difference between the new rate and the old rate? So give that a little thought. I think this one should be a bit simpler. How do you feel about this one? Probably should have given you the Henry's law constant, right? But if you plug it in there, should be able to get it. Okay. This time I just went ahead and left up the solutions that I did last time. So if we make some comparison between our initial rate versus the 1 atmosphere rate, what we really need to do, and that's kind of what I was highlighting here, is we really just need to compare the difference between these two equations. And the only thing that changes is the concentration of our gas in the liquid, of the oxygen in the liquid, at equilibrium. So the only piece that changes is the Cl star, right there. So that's going to be the piece that we need to calculate in order to solve our problem, but we do need to put everything that we do know in terms. So what we're given is that we have some bubbles, and that when we make this change, nothing about the bubbles change. So that means the Al is constant. Essentially, these will be canceled. The Kl is constant, so essentially those will cancel. So what we're going to be left with, and we can compare this either way. We can compare the new over the initial or the initial over the new, and just at least see the ratio between them and make some comparison, right? I think that's the most logical way to do it, one way or the other. So we could say then that it's going to be essentially the equilibrium condition when we are comparing this equilibrium with air versus the equilibrium with pure oxygen. But it's the equilibrium minus the 4 milligrams per liter that's there. So we'll get some concentration differential and just simply make the ratio. So that means that all we need to do is take the values here and say, well, the dissolved oxygen at equilibrium initially should be the 0.21 atmospheres divided by that Henry's law constant. So I should have given you this, right? The 769 atmospheres per mole per liter. That gives us that 2.73 we saw a minute ago, times 10 to the minus 4. We can convert that to milligrams per liter if we want to, or we could just as well keep it all as moles per liter. We do the same thing for dissolved oxygen at 1 atmosphere to get the concentration of the liquid phase, the Cl star, for the 1 atmosphere case, so fully 100% oxygen gas being bubbled, and then we get 41.6 milligrams per liter under these conditions. So then what we do is take that ratio. So 8.74 minus 4 milligrams per liter divided by 4.16 minus 4 milligrams per liter. Would have been fine to leave all these in moles per liter. Should come out to the same ratio. And that would be about 1/8. So essentially the pure oxygen scenario is providing about just under 8 times faster of a gas transfer rate. Okay? Or the air way is doing 8 times slower, or 1/8 of the speed. Does that make sense? So the point in the problem itself that says immediately, so at that instant, really that's just simply indicating that we are making an exact comparison to what it was doing to some new condition right there. All right. How does that feel? A little better? All right. Okay, so that brings us to chapter 6, and I'd like to really discuss a bit about the case where we have an aerator type system. So a moment ago we did some with spraying air into the water into the air and then blowing some bubbles into the water. So these are our two cases that we could describe. I mentioned them earlier, case 1 and case 2. Case 1 being gas transfer in systems with a well-mixed liquid phase. So this is things like aeration. Case 2 would be gas transfer in systems with spatial variations in the concentrations of both solution and gas. Whereas the first one, you see the concentration of the liquid at least is well mixed, so that it should be uniform. Okay? So the liquid concentration is uniform here. Gas may or may not be. And in this one, they're variable. And so we're going to focus on case 1. Okay. And again, we have this equation for our rate. It's going to be that overall gas transfer constant times the surface area concentration times that driving differential there for the rate of a gas entering a liquid. Okay, so if we think about one of these case 1 examples, an aerator. We might be adding in a gas, bubbling it in, and the bubbles will be rising and eventually leaving. That would be a typical system, and we have the liquid concentration should be well mixed, right? That's the deal with the case 1 systems. Now, by the way, just to kind of call back to the oxygen example, as we saw, our oxygenation works a lot better if we use pure oxygen, but that's a little bit expensive. It's a lot cheaper to just blow air than to blow oxygen, and usually it's determined that it's more than 8 times cheaper, right? Because something like 8 times the difference would be what mattered. If it was, twice as expensive as just air, then maybe we do it because we have a big impact, right? But it's not typical to do pure oxygen unless there's some special condition. But it is something that people have experimented with before. All right, so then we have a system where we have gas transfer happening as bubbles are passing through our reactor. And essentially, we will typically envision this as a well-mixed system. It can be batch. It could also be in a CSTR type of a system, and a steady flow of the gas. So we'll have some flow rate of the gas. The flow rate leaving of that gas should be pretty similar. Even if we have some transfer, it's usually going to be pretty small in the scheme of things. So it's usually the total volume or total flow rate of gas is approximately the same. So we'll say QG coming in and QG going out in that sense. Then we have a concentration in the gas phase going in and a concentration in the gas phase going out, and that's the part that we would expect to change. Especially if we're, let's say, sending bubbling oxygen from the air through our system, we're probably going to have a slight bit less oxygen here, assuming we've got some gas transfer going in. Okay, so with the depth, there are a few things that can change. So pressure, of course, the deeper we go, the more pressure we have. It's possible to have temperature changes in most of our engineered systems. We probably wouldn't have temperature change within the volume, but if we imagine that there could be a temperature differential between the gas and the liquid, right? So that's possible difference there. Usually we'll probably just keep things the same. Bubble sizes can potentially change, especially if you go deep. Then your bubbles, you'll have some gas, but it'll be compressed by the pressure, right? So that can be a deal. And we can track essentially most, if not all of that, with the ideal gas law, right? We can say that our concentration in the gas and moles per liter would be the moles per volume, and that would correspond to the P over RT. If you've ever learned anything about scuba systems and scuba diving, you really have to know this kind of stuff, right? How are your gases going to work? How much pressure do you need to actually breathe from it at depth when you have so much pressure on your body? So deep scuba diving gets to be quite a complicated task in terms of getting your gas mixtures correct. And turns out that if you go too deep, then your typical oxygen concentration that you would have, you end up getting some problems because your typical air mixture, you'll be pushing too much nitrogen into your blood. And then suddenly you get some problems with that. I think it's called nitrogen narcosis or something. So you have to actually replace some of the nitrogen. I think they do with helium. But you don't want to do too much of that. So if you go too deep, you have to change things again. And then when you're coming back up, you have to go very slowly and kind of do the backwards with all these mixtures. So scuba diving can get really complicated if you're trying to go very deep. But all of that relates to this type of thing. Of course, most of our systems won't be dealing with that, but you can imagine if something releases a gas down at the seafloor, could have some big consequences of how that will change as it goes upwards, right? So a little picture of an aerator, and even here maybe you can see the bubbles might be getting slightly bigger by the top. I don't know, might just be them kind of agglomerating together. Okay, so let's talk about the physical aspects of these bubbles. If we say we want to know something about the pressure from the water column, we can actually track that very simply by saying the differential of the pressure per differential of height. So dP dz, if this is z, is going to be equal to the acceleration due to gravity times the density of that fluid. Okay, so this works in the atmosphere. This works underwater. This is a feature of density and liquids, right? And we can treat the atmosphere as a liquid. So that can allow us to obtain or to understand what's our pressure at some depth. And we can basically write this as pressure over height would be equal to our density of the liquid times acceleration due to gravity. Okay, so we can then relate some volumetric flow or volumetric flow rate to pressure and temperature. And this will become very important because we need some way to talk about how much air or gas are we applying. Right? We want some standardized way to say we are flowing, we are blowing X amount of air into our system. Our blowers have an operational capacity of Y, of some number, right? So we can say the Q, the flow rate for our gas, we can kind of put it into standard terms by accounting for standard pressure divided by the current pressure. So a wastewater treatment plant doing an aerator up in the mountains of Colorado might have a different scenario than the standard 1 atmosphere we expect at sea level, right? So if we have some change there, we could say, we could account for it, for the pressure and the temperature by multiplying the ratios of the standard pressure divided by the temperature and the temperature divided by the standard temperature. So standard pressure would be 1 atmosphere. That's a condition at kind of sea level. And the volumetric flow, Z is the depth. T, of course, is that temperature. Okay, so we have these standard conditions, and we can get, we can expand this by saying this will be the pressure at the surface times the temperature, so the numerator is staying the same. And then down here, instead of instead of just having the pressure, we could say it's the pressure plus whatever depth we're at, essentially. So this little piece, the T over T standard, that's staying the same. And so this part, we are just taking and saying, all right, another way to write pressure would be pressure is equal to the pressure at the surface plus, what is this? That's the density of the liquid times gravity times Z. So that's the P that is current right here. So essentially what we're doing is if we are going at depth, we actually have to account for the fact that we have 1 atmosphere at the surface of the water plus the pressure from the depth of the water. So this would be from the water. Whereas this pressure would kind of be the total. So maybe we should write that as the atmosphere plus the water. Okay, so just kind of saying we have a way to find a flow rate and standardize that flow rate given pressure and temperature conditions. Pressure meaning depth, really. Okay, we have a particular name for that. That would be standard cubic meter per hour. If we do that and we're working in cubic meters, and typically the standard temperature, usually it would be 25 Celsius, but in this particular case, for this SCMH, I think 20 has been the designation. At least that's what the book is saying. Feels like it should be 25, but I'm gonna stick with the book. All right, so we can have a few relationships, the table full of them, essentially being derived from what we just talked about, this relatively simple equation here, pressure per depth. It's gonna be, okay, well, how much mass of our liquid is stacked up on top of it, right? If we looked at it that way, we would, that should make some sense. And if you've taken any sort of air quality course, you've probably seen that exact thing to describe our pressure in the atmosphere. Okay, so we could have pressure versus depth. We could have bubble volume versus depth accordingly. We could look at volumetric gas flow rate versus depth. Again, if you're scuba diving, that kind of thing might become quite important, right? How much air are you actually going to be able to breathe? How quickly are you going to go through the air that you have? How much pressure do you need in your tank? And at what pressure can you no longer draw breath because there's still some gas in there, but it's not enough, right? There's a lot of big questions there. Okay, bubble diameter versus depth and bubble area versus depth. All of these features, I'm basically just saying we could see the geometry and relate it to the pressure accordingly and have these formula. Okay. All right, so let's take a look at an example. And I copied and pasted each of those in case we need them. So here we have a diffuser. It's injecting air bubbles that are 1.2 millimeters in diameter into water at a depth of 4.5 meters. The gas rate is reported as 120 standard cubic meters of air per square meter of diffuser area per hour. The water and air are at 5 degrees Celsius. Each diffuser has an area of 0.025 square meters, and the diffusers are installed at a spacing corresponding to 3 diffusers per square meter of floor space. Okay, so A, what is the true air injection rate per unit floor area? So that's a meter cube of air per minute per square meter of floor area. It's a mouthful. So that's the first question. Go ahead and read the other two and then we'll come back to that. So B, what are the average diameter, surface area, and volume of the bubbles in the tank? and C, estimate the surface area concentration in the tank. Okay, so first thing I would do is draw some sort of a little diagram so I understand what the heck this is talking about. Right, that's what I like to do. And then for A, once we do that, we're just segmenting off 1 square meter, and we were given something in square meters, and so we'll take a look at that. I'm going to flip backwards for a moment so that we can take a look and identify which ones of these equations were relating the surface area and volume for the bubbles. So diameter, surface area, volume. Bubble diameter, bubble surface area were the last two, which is and bubble volume was that second one. All right, we have a few minutes, so give this a shot and we will see if we can get through part A in about 5 minutes. All right, let's take a look. First of all, drawing some sort of diagram, and I didn't do a great one here, but it describes we have this larger tank and we are segmenting off some piece of it. It says there are 3 diffusers per square meter. I don't know if the 3 matters at all, but the point would be to have some of these diffusers, which are probably strung out on pipes that are just distributing air to each of these diffusers. And so we could arbitrarily say, okay, here's 1 square meter, and on average that'll have 3 of those guys. So like I said, I didn't draw it exactly to scale because any way I cut this, unless I cut it like that, then we don't have 3. So let's just say there's our square meter, not very square, but it's a meter, and call it good. Okay, so just some sort of diagram depicting the fact that we are segmenting off some portion of it. Fine. So the question is asking, what is the true air injection rate per unit floor area? So this should actually just be a calculation in that standard cubic meters per hour type of deal. And so that's going to be, I think what we'll need is this volumetric gas flow rate versus depth. So, wrong way. So here, and I should have highlighted this for you, essentially we're going to use this equation to account for our 4.5 meters deep that we have, right? And apply that to solve A. So this would be our QG at some depth. And I think I've just got the book solutions. We've got 3 minutes, so we're just going to read through their solutions on A and there. So here it says, so nominal airflow rates are given, the standard conditions at the surface, 1 atmosphere at the surface and 20 Celsius. So the given rate must be corrected, and if we think about it, we are going deeper, so more pressure. That means we're probably getting less volume, right? A bubble that is pressurized, as it depressurized, should expand. So we'll have a smaller volume than we would have at depth. Okay, so then that's equation 6.5. We can solve, and this the product of our density times gravity will give us 0.098 atmospheres per meter with 4.5 meters depth. Okay, so therefore our actual flow rate for this air at depth turns out to be, we do these calculations, do that correction with the temperature and the density and the depth to be that 120 that was given times 1 over 1 plus that 0.098, and also combining the difference in temperature, 5 degrees Celsius compared to the 20 degrees Celsius, putting those into kelvins to have them in absolute. Okay, so at the end of all that, we get 79 cubic meters per of air per hour per square meter diffuser space. So per diffuser, we can divide that by 3 because we were told that each diffuser, there are 3 diffusers per square meter. Okay, so that gives us, at the end of the day, so the flow rate, I guess that was per diffuser, I'm sorry. So, but since we have 3 per square meter, we can then find the flow rate per square meter of floor space as that 79 times the 3 times this amount per surface area of diffuser is how we're ending that. So that gives us 5.92 cubic meters of air per hour per square meter of floor space. A lot of little conversions there to answer the problem as it asked, but it is pretty straightforward. Once we recognize, okay, 3 per square meter, blah, 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 this much area per diffuser, blah, blah, blah. It's all right there. Does that make sense? Okay, so I think the tricky part would be recognizing, okay, how are we dealing with that conversion? But it's just a matter of taking that equation and manipulating it. All right, so we'll end there. We'll do a little more air on Thursday and then get into adsorption, and I'll remind you about next week at that time. Okay, see you Thursday.